Okay, we have our next definition in chapter 11. We just saw that finite normal extensions are helpful, right? They're ones where we can sort of somewhat simply construct elements of the Galois group. The elements would be interchanging conjugate expression, not interchanging, but sending conjugate roots to conjugate roots. So normal extensions are great because we can actually really get in and actually construct elements of the Galois group without getting our hands too dirty. Most extensions are not normal, but even if they're finite. So we might want to know, how do you normalify an extension? So suppose we had a finite extension that we're starting with. Suppose it's not normal. So for example, in our head, we know of a lot of different extensions that aren't normal, like q inside of q adjoin the cube root of 2. Pick any of them. That's not normal because it only has one of the roots, the cube roots of 2. It doesn't have all of them. But we can normalify it. So what does that mean? Well, it's called taking a normal closure. So a normal closure of the extension L over K is an extension of what? Well, L doesn't have enough in it if it's not normal, right? We're missing some of the roots of some polynomials. So this is going to be extension N of L. We're going to further enlarge L such that we enlarge it in such a way that now the big extension, so in our head we have K sits inside of L, but L doesn't have enough, so we have to make it bigger. So we have this big extension N over K. This should now be normal. We want to enlarge it in such a way that we have something normal. And two, we have to have a smallest condition, because one way in which you can enlarge an extension to make it normal is you just put a C there. Right, and I could just put all of the complex numbers. I've added in all the roots, so I'm good. I'm normal now. But doing so won't, in general, also result in a finite extension because we've added like way too much. So we have a smallest condition. So the smallest condition, the second condition, is if you have another extension in between them, and so M sits in between L and N, and M over K is normal, then M equals N. And we should think about this, well, the first condition as being the normality condition, and the second condition as being the smallest condition. Okay. All right. Let's prove a theorem. Let's do an example first. Example. And then we'll prove a theorem. Let's look at the example that I just wrote down. So Q inside of Q adjoin alpha, where alpha is a real cube root of 2, or any cube root of 2, is not normal because it's not a splitting field. We're missing omega alpha and omega squared alpha are not in Q adjoin alpha. Again, where omega is any primitive cube root of unity. I can take the standard one if I want. So how do we make it normal? Well, we add in the remaining roots. So let's set N to be Q adjoin alpha, and then we saw a bunch of times to get the rest of the roots, we just have to add in omega. Then what? Well, then N over Q is normal, as it's a splitting field. And splitting fields are always normal. The extension you get from a splitting field is normal. Okay, and we have added the smallest possible amount to get something bigger and normal. So if you recall, omega all we're really adding in with omega is we're adding in the square root of 3i. That's all we're adding in. So we added in just a quadratic extension. There's nothing that sits in between u and the quadratic extension. So let me say that a little bit more mathematically. So there's no smaller extension. So there's no m that sits in between them, as the degree of Q adjoin alpha omega over Q adjoin alpha is 2. So either m is Q adjoin alpha, in which case it would not be normal, or M is Q adjoint alpha omega, in which case we have the smallest condition. So our normal extension is right here. Our normal closure is right here. So let me write it out. Q adjoint alpha omega is the normal closure Oops, misspelled that. Of Q adjoint alpha over Q. All right, there's still time here. Let's prove a quick theorem. I say it's quick, but we might take a little bit of time. Suppose L over K is a finite extension. In C, everything's in C. Then there exists a unique normal closure, N of L over K, which is still finite. So we found a way of extending our extension, the larger field, so that the large one is normal, N over K is normal, and we've maintained the finite condition. So this N over K is now finite. And so now N over K is a splitting field, and we have all the stuff that we said about splitting fields already. So this is a wonderful theorem. All right, let's prove it. Proof. Let x1, since it's L over K is finite, there's finitely many elements in a basis. Let these guys, x1 through xn and L, be a basis for L as a K vector space. Since L over K is finite, since it's finite, each of x1 through xn is algebraic. So it's the root of some polynomial over K, irreducible polynomial over K. Let's let M1 through Mn be the minimal polynomials of the basis. So M1 is the minimal polynomial of x1 and so forth. Let's set F to be the product of the minimal polynomials. And let's let N be the splitting field of F. Okay, so we took a basis, those elements x1 through xn, maybe if we look at their minimal polynomials, we're missing some of their conjugates. So what we do is we just take the minimal polynomial and we add in all of the conjugates of all of the minimal polynomials. That's what F does, and that's what taking the splitting field of this F does. All right, then N over K is finite, certainly, and normal. All right, you might think we're done, but we're not done. To be a normal closure, it has to be normal, and if there's a smaller one, it must be that it's actually this one. So we haven't got to the smallest condition yet. All right, so let's do the smallest condition now. Now suppose that we have a smaller one. So L is contained in P is contained in N with P over K normal. Then each of the Mj has a 0 in P. Because that 0 is in L, because x1 through xn were in L, and L is a subset of P. By normality, P has all the zeros of Mj. So P must, for each J. So P must be obtained from L, or from K rather, by adding in all the zeros of the m's. But that's how you construct n. That's what n is. So P must be equal to n. That's how you construct a splitting field. You add in all the zeros. So P is n, and therefore n is a normal closure. And let me just point out, this is constructive. It tells you how to find the normal closure. This is a recipe. It says, hey, to construct the normal closure, write down a basis, add in all the conjugates of the elements of the basis. Find their minimal polynomials, add in all the roots. Right, so it's a recipe. Okay, so we showed there exists a normal closure, which is finite. We now need to show uniqueness. So for uniqueness, suppose we have two, m and n are two normal closures. Since f splits in both m and n, why? Well, they have m and n are both normal. They have the roots x1 through xn in them because L is a subset of both of these. Right? L is a subset of both of these. And by normality, they must have all the other roots. So f splits here. So it has all the roots of f. So each of m and n contain the splitting field, which was what we called n in the previous part. But the splitting field is already normal, and it's would be smaller than or equal to these. By the smallest condition in the normal closure, they must both be equal to the splitting field. All right, so sorry, that proof took a little bit longer than I thought. But what do we learn here? Normal closures are unique. When you take the normal closure of a finite extension, it stays finite. And there's a recipe for constructing it. You just add in the remaining roots that you need.